In this video, we're going to talk about cells, batteries, and EMF, which is the electromotive force. First, we want to talk about electric charge. Electric charge is a fundamental property of matter, and there are two types of electric charge that we come across, positive and negative, and charge is always measured in coulombs. Electric charge, we think of the fundamental charges, and this picture here shows what we consider to be a proton, which is the positive charge, and we have an electron here, which is a negative charge. And the value of this is 1.6 times 10 to the negative 19 coulombs, and the value of the charge on an electron is negative 1.6 times 10 to the negative 19 coulombs. And so this is called the fundamental charge, and we give it the letter E. So the fundamental charge is negative 1.6 times 10 to the negative 19 coulombs. We can categorize materials into groups as insulators or conductors. So an insulator is an object that does not conduct electricity easily, wood, rubber, things that insulate. A conductor allows electricity to flow easily, which is things like metals, so copper, gold, silver. These are very good conductors. So what distinguishes between insulators and conductors is the amount of free electrons that the material has, which is basically how easily can the electrons move through the material. A cell is an object that causes the movement of charged particles, and for us it's going to be electrons, and we call this electricity. So a cell is something that creates electricity. A battery is a container with one or more cells inside. So in science, we do use the word a lot of cells for a lot of different things, but when we talk about electricity, we're talking about a device that creates electricity. There can be different types of cells, but two main ones we're going to talk about are chemical and solar. So a chemical cell converts chemical energy into electric energy. A very basic idea of this, we're not going to get into too much detail, but basically a chemical cell has two different electrodes here, and they are connected somehow. And what happens is there's some chemical reactions that take place inside the cell in the electrolytes, which causes the transfer of electrons to occur. And we say that one side is positive and one side is negative, and that current will flow from one to the other if we connect it on the outside. And so that's a very basic description of how chemical cells work. A solar cell is an object that converts light energy into electric energy. And so this is another simplified version here. But what happens is in this material here, light energy comes in, and if it's the right amount of light energy, it excites an electron. And if you create a connection here between the two sides, what you can do is also induce a current from one side to the other. And so that's, again, a very basic overview of how solar cells work. When we make circuit diagrams, so we're drawing what's going on in a circuit, we use circuit symbols to simplify this thing. And so for a cell, this is the symbol for a cell. And this would be the same for a chemical cell or a solar cell or any type of cell. But the key thing we need to keep in mind here is that the long side of this diagram here is the positive side of the cell, and this is the negative side of the cell. And then these parts here, these represent connecting wires, which eventually, when you get more complicated circuits, you attach to different objects. Electromotive force, which we call EMF, is the energy transferred to an electric circuit per unit of electric charge. The symbol we use it is this epsilon symbol, and we measure electromotive force in the unit of volts. To calculate the electromotive force, we divide the energy provided to the circuit by the amount of charge passing through it. Now we'll do some questions based on this material, see if we get a good understanding of what's going on here. As we do these questions, I recommend that you pause the video and attempt to answer them for yourself and see how you do. Example 1, insulators cannot conduct electric current because A, they do not have electric charge carriers, B, they have a low density of charge carriers, C, the charge carriers require a large amount of energy to move, or D, they allow charge carriers to move freely. So we can start eliminating some of these answers. A cannot be correct because all objects are made of protons and electrons, so they all have charge carriers of some sort. B is an interesting one. They have a low density of charge carriers. I'll come back to that one. See, the charge carriers require a large amount of energy to move, and D, they allow charge carriers to move freely. Well, that's a conductor, not an insulator. So it's between B and C. And it turns out the correct answer in this case is C. Now, materials like wood have an equal number of protons and electrons generally. So there's not as if there's a difference in the density of charge carriers. But the difference between wood and copper, for example, is that to move the electrons through copper, it doesn't require a lot of energy. Whereas to move the electrons through a piece of wood requires a tremendous amount of energy. Wood can eventually conduct electricity, and you might have seen examples of this, or if you think of lightning striking a tree, the electricity does eventually travel through the wood, but it requires a huge amount of energy to move. Example 2, a battery provides 3.1 microjoules of energy to 15 nanocoulombs of charge between the terminals. Determine the electromotive force of the battery. All right, so we have an amount of energy here. We have 3.1 microjoules, which is the same as 3.1 times 10 to the negative 6 joules. And then we have 15 nanocoulombs of charge, which is 15 times 10 to the negative 9 coulombs. If we want to calculate the EMF, we have to divide the amount of energy by the amount of charge. So we do 3.1 times 10 to the negative 6 divided by 15 times 10 to the negative 9. And we get an EMF of 206.66 volts. And I will round this to two significant figures. So the EMF in this case is 210 volts. So the key thing to remember here is that a volt is equal to a joule per coulomb. If a 1.5 volt battery provides 4 joules of energy over a time period, estimate the number of electrons passing through the battery. This is an interesting question here. It's given us the EMF, so we know the EMF in this case is 1.5 volts, and we know that the amount of energy is going to be 4 joules. And I'm going to write that as W because work is a change in energy. So I'm going to write that as W, 4.0 joules. So a couple things we need to figure out. First thing from this, we know we can figure out the amount of charge. And charge has a symbol Q. And so we could figure this out. We can use the formula EMF is work per unit charge. This is the definition of EMF. And we can use this to calculate charge. So charge is going to be the 4.0 joules over 1.5 volts, and so we have a charge of 2.67 coulombs. Now we have the charge, but we don't know how many electrons there are. However, we do know that electrons have the fundamental charge, which is 1.6 times 10 to the negative 19 coulombs, and we can use this to calculate the number of electrons that have passed through. So the number of electrons is going to be 2.6 divided by 1.6 times 10 to the negative 19, which gives us 1.7 times 10 to the 19 electrons. So as you can see, it's quite a large number of electrons that pass through this battery in this time frame. In summary, charge is a property of matter. It's measured in coulombs. We have positive and negative. The fundamental charge is 1.6 times 10 to the negative 19 coulombs. Conductors have freely moving electrons, while insulators do not. We have two main types of cells, chemical and solar, and both of them convert one type of energy into electrical energy. And then the electromotive force is defined as the energy transferred to a circuit per unit of charge.